The last model we're going to discuss is known as the quantum mechanical model, and it takes care of all the problems of the Bohr-Rutherford model. It incorporates the wave-like characteristics of electrons. So the father of it is known as Erwin Schrödinger, and what he did was he took the Bohr-Rutherford model. Remember, Bohr was really good at describing an electron's energy level, not so good at describing the position of an electron or its path. And what Schrödinger did was he wanted to be able to say with more accuracy where an electron is. So what he did was he took a new equation known as Schrödinger's wave equation, which allowed him to predict the location of an electron using statistical probabilities. What he did was he solved an equation with a particular set of variables, electron speed, that sort of thing, and got an answer of where the electron was. And then what he did was he made what's called a density plot. And here's an example down here where the red is the nucleus of the atom, and he put a dot where the location of the electron was, where he solved mathematically. Then what he did was he changed the variables in the equation slightly and solved for the location of the electron again and put a dot there. So these pictures are intentionally grainy. Each one of these dots is a solution to a mathematical equation. Now what Schrödinger did was he found that there's an infinite number of mathematical solutions. And so he said, well, there has to be some cutoff region, right? Where would you find most of the answers? And what he did was he chose a 95% cutoff, where 95% of the time you will find the answers to his Schrödinger's math equation within this circle. But remember, atoms are not two-dimensional. So what he was really doing was he was solving these equations in 3 dimensions. And so he found a region where 95% of the answers were found and contained inside of this sphere. So it's important to note that this is not the path of the electron. It doesn't travel around on the outside of this ball. It's also not a container that the electron bounces around in. Theoretically, the electron can be anywhere in the universe, but 95% of the time, you will find an electron somewhere in this region. Schrödinger called these regions of probabilities atomic orbitals. So he took the Bohr word orbit and stuck AL on the end. Whenever you see pictures of Schrödinger, he's usually standing in front of a desk with a big pile of books behind him. Those are the notebooks where he handwrote all of his calculations to figure out where these regions of probability are. And he noticed, depending on how much energy the electron had, the region of probability had a different shape. So a code system was developed by scientists to describe the different sizes and shapes of the regions of probability where you would find electrons. The first quantum number is known as the principal quantum number, or little n is the symbol. It describes the orbital size and how much energy the electron has. Now, this was taken directly from the Bohr model. When n equals 1, it's in the first shell. When n equals 2, it's in the second shell. The higher the value of n, the larger the orbital is, and the more energy the electrons have. So that means the faster that they move. The total number of orbitals for each energy level can be quickly calculated by using the equation n squared. So if n equals 1, then I only have 1 orbital. But when n equals 2, it actually means I have 4 orbitals to place electrons with that same amount of energy. Now, the greatest number of electrons possible in any energy level is given by the equation 2n squared. So this is where the 288 rule that you learned in grade 9 becomes a little untrue. In the first energy level, when n equals 1, you can only have 2 electrons. In the second energy level, when n equals 2, you can have 8. But in the third energy level, when n equals 3, you can actually have 18 electrons in the shell. The next quantum number is known as the orbital shape quantum number because it tells you what shaped orbital you have. It has to equal a positive integer that ranges in value from 0 to n minus 1. So for example, if n equals 1, first energy level, then L can only mathematically equal 0. That means you only have one shaped orbital. If n equals 2, L can possibly equal 0 or 1, which means that at the second energy level, there's actually two different shaped orbitals available to put electrons in. If n equals 3, then L can equal 0, 1, or 2, giving you three possible shapes for your orbitals. Now, you'll want to add this to your note. How we tell what orbital shape we have is the following. When L equals 1, it means you have an s orbital. S stands for spherical. When L equals 2, it means you have a p orbital. When L equals 3, you have a d orbital. And when L equals 4, it means you have an f orbital. That's the code system you need to learn. So what do these things look like? You have a diagram on your note here. So s orbitals are spherical. And this diagram, some people get confused. Here I have L equals 0 each time, but I have my n equals number increasing, so my spheres get larger and larger. So this would be the s orbital for the first shell, the second shell, and the third shell. P orbitals kind of look like peanuts or dumbbells. Now you notice on our diagram here we're on the second energy level and L has to equal 1. It equals that for each one of these diagrams. Because they're peanut shaped, they can actually stack on top of each other, so you can fit more than one peanut in each energy level. D orbitals, I like to think of them as looking like daisies. They look like flower petals. Some people describe them as two peanuts crossed or two dumbbells at 90-degree angles. Except for this last one here, which is kind of weird. It's a peanut wearing a hula skirt. The last quantum number is known as the magnetic quantum number, or symbol ML. It describes the plane or the orientation the orbital is in. Remember, we're working in three-dimensional space. So in math class, you would have, if we're talking about graphing, you would have horizontal line being your x-axis, and the vertical line being a y-axis. In order to get 3D, what you would do is you would create another axis that comes out of the page and goes in behind the page, which is known as the z-axis. So that's how you get 3 dimensions. So what the ML value tells you is which axis or what orientation in three-dimensional space is your orbital. Now, they are coded so that ML values are integers that range from -L to +L. And that's the easiest way to come up with them. Now, there is another math equation you can use. You can figure out the number of ML values by using 2L plus 1. Now, what that tells you is it tells you how many orbitals of the same shape you have at that particular energy level. So that comes in handy too sometimes. This concept organizer down at the bottom of the page is out of the old textbook. It's really handy. What it does is it shows you all the possible quantum numbers for the first 3 energy levels. So here, if we have a look at n equals 2, so I'm at the second energy level. So I've got electrons that are moving fairly quickly and a little bit further away from the nucleus than in the first shell. Now, at the second energy level, L, the second quantum number, can equal 0 and 1. So what it's telling me is I have both S-shaped orbitals and p orbitals in the second energy level. Now, when n equals 2 and L equals 0, I can only have an ml value equal to 0. That means that I only have one s orbital because there's one number there. But when n equals 2 and L equals 1, remember ml can range from minus L to plus L, so it gives me three values, minus 1, 0, and plus 1. Because I have three possible numbers here, it means that I have three possible p orbitals to put electrons in the second energy level. Remember the quick math equation? To figure out how many orbitals you get at each energy level, it's n squared. So I should have, at the second energy level, 4 orbitals. Here's 1, 2, 3, 4 orbitals corresponding to the 4 ml values. Now, quantum numbers kind of give you like a GPS coordinates, an address. Sort of like what country you're in, and then the second one gives you what city you're in, and ml value gives you what neighborhood you're in. So if we take a set of quantum numbers, it gives us a lot of information of where that electron is. So let's look at an example. Let's say n equals 3 and L equals 1 and ml equals plus 1. What this tells you is that because n equals 3, we're in a fairly large orbital and the electron is moving pretty quickly. Well, what shape is that orbital? Well, L equals 1. So when L equals 1, that means I'm in a p orbital. And because n equals 3, it's going to be a pretty large peanut. Now, ml, that equals a positive 1. Remember, when L equals 1, our three possible ml values are minus 1, 0, and plus 1. This corresponds to the x, the y, and the z axis. So with an ml value of positive 1, I have a pretty big peanut lying right on that z axis, coming out of the screen and going into the screen. Now remember, the quantum mechanical model doesn't tell you exactly where the electron is. We know with high accuracy how fast that electron is moving or how much kinetic energy it has, but we don't know quite where it is. What Schrödinger did was find out where the electrons were most of the time and help develop this code system of quantum numbers to communicate it quickly and easily with just 3 digits. Make sure you check out the wave-particle duality video. It goes through some of the major applications of technology that came out of understanding electrons as being waves.